I was
Okay.
The hand is Peter.
Since I'm recording this, I'm going to go back to the beginning and we're going to go fast through the first part just to set up the explanations. Big picture. Okay, hopefully Ackerman doesn't slow me down too much and I can get to where we need to be so that you're even with the other class. But I'm not like holding my breath. Okay, thermochemistry. Thermodynamics.
I just realized where it is.
Are we recording?
Yeah.
Okay, the big picture in this unit is, will a reaction occur spontaneously? And do you know what spontaneous means?
Just happens out of random.
It's not necessarily random, but it doesn't require outside assistance. It will just happen. And there are two factors that will affect whether something is spontaneous. Enthalpy and entropy. So entropy is disorder. The universe is moving towards chaos. That happens naturally. It's the force of nature. There's nothing you can do about it. The second trend that would tend to make something spontaneous is things go from high energy to low energy. And we talked a little bit the other day about probabilities. Remember that? Okay, so we're going to treat those two things separately. First thing we're going to look at is high energy to low energy, or the enthalpy change of a reaction. And then we're going to look at entropy, and then we're going to combine the two. Okay? An exothermic process is a process that gives off heat. So the energy is transferred from the system to the surroundings. Going from high energy to low energy. Would that tend to be spontaneous?
That would be spontaneous.
Yes.
Yeah.
You're going from high to low.
Okay. At this point, I don't want you to say that will be spontaneous.
It could be.
It could be. Based on the enthalpy change, that would tend to be spontaneous. We can't say definitively until we combine the two trends. Because the entropy change for one of those reactions shown there could tend to be not spontaneous. So we have, before we can say for sure, we have to combine the two. So at this point we're just going to say those would tend to be spontaneous based upon the enthalpy change. Okay? They are going from high energy to low energy. The surroundings is gaining in energy. The system is losing energy. An endothermic process is a process in which heat has to be supplied from the surroundings to the system. Okay? Those would tend to not be spontaneous. Does that mean they have to be not spontaneous?
No.
No.
It still happens.
You ever felt an ice pack or one of those? Yeah, ice pack. The things that trainers use.
Yes.
They break a little pouch inside there, and then it gets cold. That is an endothermic process, and it's happening spontaneously. Okay? So what does that tell us? If it's endothermic and it's happening spontaneously, then we can make a conclusion about the entropy change.
It's going from high energy to low energy.
No, the entropy change.
It goes like that, up, and then it goes back
And
to
it's moving towards higher entropy, more chaos, enough to offset the enthalpy change. Okay, enthalpy, or H, is used to quantify the heat flow into or out of a system. For the most part in chemistry, that's what we're looking at as far as the energy change. It's the most measurable, and it's the most common in a chemical reaction. Is that the only way that a system can give off energy in a chemical reaction? Is heat?
No.
Name one other.
Light.
light,
Light.
Sound.
sound.
Uh, Oh, okay, maybe. Can you think of an example where a chemical reaction gives off sound?
It goes
Where-
boom.
No.
Yeah, it's doing, yeah, sure, it's doing work on its surroundings, causing the explosion sound. You know what causes an explosion?
No.
Trying to contain the explosion and then just
A rapid expansion of a gas.
very volatile, so it tends to just.
It happens a lot with like nitrated compounds. You have NO3 and nitrate on a compound, and it produces N2 gas, and the gas expands quickly, causes the shock waves. A system can also do work. Remember when we, in pre-AP, when we combined the acid and the base, produced a gas, you had the balloon over the top of the flask?
It just randomly expanded, yeah. Well,
It did work on the balloon. It takes, you have to do work to blow up a balloon. It takes energy from you, right? Well, that chemical reaction is doing work on the balloon too, because the balloon just doesn't blow itself up. But for the most part, we're going to look at enthalpy change. And we'll be looking at the delta H. It's hard to measure the enthalpy of a system, but it's much easier to measure the change in enthalpy when a reaction occurs. Or a physical change occurs, like changing phase from solid to a liquid or liquid to a gas. Come on. All right, thermochemical equations. We've got the enthalpy change here. The heat is absorbed by the system. Is delta H going to be negative or positive?
Positive.
Why? Because it says in your PowerPoint? Why?
Because
If the system is taking in energy. We're focused on the system, not the surroundings. Okay, so if the system is absorbing energy, the system is going up in energy level, so the delta H would be positive. So any endothermic reaction would have a positive value for delta H. .01 kilojoules are absorbed for every mole of ice that melts. So we would write that equation this way, with the delta H over to the side with a positive value. Okay, here you've got combustion, methane and oxygen reacting to form carbon dioxide and water. We're going down in energy level, so energy is given off from the system to the surroundings. Is delta H negative or positive?
Negative.
Negative. .4 kilojoules are released for every mole of methane that combusts. So we would write that equation this way. Can you see it? And the delta H would have a negative value.
So,
Yes.
all exothermics will be negative and all endo's will be positive.
All exothermic reactions, the delta H would be written as with a negative value. All endothermic reactions, the delta H would be written with a positive value. Remember the 15-minute limit?
Yeah.
Oh, buddy.
Yeah, it's almost. We're at 9 minutes.
Okay, the stoichiometric coefficients refer to the number of moles of a substance. So that 6.01 kilojoules for the delta H, that would be for 1 mole of water. See the coefficient for H2O? It's a 1. If you reverse a reaction, the sign of delta H changes. The value does not. Their absolute value does not, but the sign changes. So if we know the delta H for the forward reaction, we know the delta H for the reverse reaction. Just change the algebraic sign. Okay, if you multiply both sides of the equation by a factor n, then the delta H must change by the same factor. So if we have 2 moles of water going from solid to liquid, then the enthalpy change is going to be multiplied by 2 as well. Simple enough?
Yeah.
All right, the physical states of all reactants and products must be specified in thermochemical equations.
Melissa.
Yeah, if you look at that previous slide, the enthalpy change was different for water going from a solid to a liquid than from a liquid to a gas. You have to specify the state of matter. Actually, it's on this slide. Hold on, one quick question here. Look at the difference in value of delta H for water going from a solid to a liquid, and from a liquid to a gas. Why do you suppose the delta H is over 7 times greater to go from a liquid to a gas than from a solid to a liquid?
It's giving off more heat.
Y'all hear what she said? That's not too bad.
Nobody ever
The
hears
high
it.
temperature for it to become gas. So since the change in H is dealing with heat flow.
Just think about, I don't know if you can hear her, she's very soft spoken.
Speak up.
But she said something essentially, something to the effect of the molecules in the gas phase have a lot more energy. So to get them there, it's going to take a lot more energy. They're moving around a lot. They expand to fill their container. They're not stuck in a glass, like in liquid water. Okay? They're existing at a higher energy level. So to go from that liquid to the gas takes a lot more energy. A lot more energy than to go from a solid to a liquid. It's still just sitting there. All right? All right, how much heat is evolved when 266 grams of white phosphorus P4 burn in air? So we've got our equation. Is it endothermic or exothermic? It's exothermic, we have a negative value. You want?
Today or next week?
Yeah, today, hurry up. We're busy. Okay, so this value for the kilojoules would be for 1 mole of P4. See the coefficient? We don't know if we have 1 mole, we have 266 grams. So we're going to take that 266 grams and convert to moles. Molar mass is 123.9. Then once we have moles of P4, it's 3,013 kilojoules for every mole. Huh? Wakey, wakey.
Eggs and bacon.
Eggs and bacon.
They hate that.
Okay, so 6,470 kilojoules. Why does that have a positive value?
Because everything else is positive.
Because everything. If everybody jumped off a cliff, would you?
Yeah.
I would wait to go last with about